Hey, this is Brock Lemires, and in this video, we're going to look at how to perform derivatives and integrals on a time series. So, performing some basic calculus. All right, so we are continuing looking at time series using arrays. And a time series is where you use one array to hold a time step and another to hold basically the function. So, for example, here's a sine wave, right? So you have this sine wave that sits over here, and you have one array that holds all the time steps that goes from 0 to whatever, and then you have the actual output, so the f of x. So everything is discrete, right? So it's discrete points, so it's not a continuous line. And so one of the things that's interesting is to try to perform kind of basic calculus operations on this. And if you haven't taken calculus, you don't need to worry about it. I'll just tell you what we're doing. So the first thing in calculus is called a derivative. And a derivative just means it's the slope of a line. All right. So at any given point, you're like, what is the slope of the line that is tangent to the function? Okay. So if this was continuous, you could imagine that you have this like little line that sits there, and at every different point, it's changing its slope as you move along. Well, we have a discrete set of points, so we can actually perform the derivative of it or find the slope of the curve at any given point using a simple operation where we just find delta x over delta y between 2 points. So let's apply that to this sine wave. So let's assume that the sine wave is a voltage, and let's assume time is time, which is true. All we really need to do is to find the rate of change, or the slope is basically find the difference in the rise over the difference in the run, or said another way, the difference in 2 voltage points on the y-axis and the difference of 2 time points on the x-axis. So all you really do is do delta v over delta t, and that is, by definition, the slope. That's the rise over the run. That's what the derivative is. Now, the derivative is really simple in a digital system like this, where you have discrete time points, because you really only have 2 things. What you'll learn in calculus is how to find this when you have a continuous curve. Okay, so that's really all we're going to do. So all we're going to do is, if these are in arrays, we can basically take the sine of the next point. So if we're evaluating what the slope is right here, you take basically the value here, okay, in the voltage or the sine array, subtract the value here in the sine array, and then you divide it by this t step. What's nice about this is that you can use the for loop index to actually determine that if this is I, this is going to be I plus 1. Let's do it. Now, in this example, we need a time series of a sine wave. And so in order to make this video shorter, what I need you to do is go get your time series that we did in the last video, okay? So what I say is, instead of creating one from scratch where we're gonna spend 10 minutes building up the sine series of this, or the time series, just go ahead and copy your time series.c file from the last video to one called calculus. And I'll show you how to do that. So I'm gonna come over here, let me grab this, and oh boy, let me grab my shell here. I'm logged in, and I'm going to go into my mod 08 code along, and I take a look at all these files I've been creating. And what I want is this time series.c. So I'm going to do this. I'm going to go copy cp time series, and I'll just go ahead and autocomplete with the tab. And I want to copy that over to calculus.c. Okay. And now I look at it, I have calculus. Okay. So I'm going to vim calculus, and now I'm up and running. All right. Now, to make sure that everything's cool here, we'll go ahead and do this. Playing with calculus. All right, boom. Now we're gonna come over here. Let's compile this and make sure we can even do what we're trying to do. So I'm gonna change into mod 08, and I'll go ahead and say, let's go ahead and GCC calculus, direct the output to an executable called calculus. Merci. Let me move this over so it's not as, so it's calculus. Good to go. Oh, whoops. It uses the sine function. So we got to do -lm to link the math.h header file. We did it. Let's do it with warnings all. Good to go. Run this thing, calculus, and we should get time. We get the voltage, and we're good to go. So now what I want to do is I want to add a function to this, which will actually calculate the derivative of it. And I want to print the derivative over here as a separate column. Okay. So I'm going to go through my code, and you remember what we had. We had our includes, standard IO and math. We had our pound define macros that set the start and the stop of the time axis. We set up our arrays right here. If you didn't do the code in the last video, just type all this in. We filled our time array, we filled our sine array, we printed the results. So before I print the results, I'm going to go ahead and add a little bit more functionality to this to calculate the derivative. So I'm going to go ahead and say find derivative. Now remember, this is a time series, meaning that now we're going to create an array that is going to hold the derivative values. And I'm going to call this dv dt for change in voltage over change in time. And it is going to have n points, the same number of points as our time array t and our sine array v sine. All I'm going to do is simply go for I equals 0, I less than n points, I plus plus. I'm going to iterate through each element in the array, and I will simply do this. dv dt equals, and I'm going to go up here on the numerator, and what I'm going to put is the change in voltage, which is simply v sine, that's the array that's already been created up here, and I'm going to say I plus 1, so that's the next value in the function, minus v sine of I, which is the current point that we're at. And then all I'm going to do is divide that by the change in time, which is nothing more than t step. And remember, t step was calculated up here, where all we did was said, okay, I'm going to take these macros and say max time minus min time divided by n points minus 1, and I got t step. So we already calculated the delta in time. And so it's like, wow, that was really easy. I thought calculus was hard. All right, so now you're looking at me going, what a dv/dt, aren't you going to put like an index in it? And the answer is absolutely. So there it is. I've filled up that array. Now I want to print that, but let's print it. Let's print it along with this right here. Okay, so I'm going to basically try to print it as another column here. I'm going to do something that we haven't done before. After I put this comma, I'm actually going to do a line return, and that is acceptable because this is considered still one statement until C sees the semicolon. So that allows me to basically have more information when these printf statements get really long. Okay, so here's what I'm going to do. I'm going to go ahead and I'm going to do this. I'm going to say insert, and I'm going to make this a little more concise. Okay, so I'm going to get rid of the spaces here just because it's getting a little nutty. And what I'm going to do here is I'll still put tab, but now what I'm going to do is say print the value of dv dt at I, but I want to print I. I physically want to print the value of I. So I'm going to do a %d format specifier, and I'll then put the variable as to substitute in there. And then what I'm going to do is say equal, and then I'm going to actually print the value of the array, which is a double. So I'm going to do format specifier, long float, but let me go back and let's make it with 3 decimal places. Okay. Now I should have it. So now I've got t, v sine, dv dt, and in each of these, I'm going to print the index integer within the little text. So now all I have to do is go, okay, print I to go there, and then we'll print dv dt at I, and we are good to go. Okay, so I come down here and I'm going to compile this little buddy, GCC it, and run it. And lo and behold, look at what we have. So you have numbers, and it's like, are they even close? Like, are they right? Like, I can show you what the answer is supposed to be. They are right. But more importantly, look at the sine wave and tell me if you think they're right. So you come along, and when you start right here, you basically have a line it looks like it's about a slope of 1. 1 is where it's going 45 degrees up. Then as you go up over the arc of the sine wave, it's going to flatten out to be a slope of 0. Then it's going to start going like this and have a negative slope until it gets down here where it will again have a slope of 0. And then it'll start edging back up until it basically has a slope of 1 again. So if you look at this, it starts at 1, goes down, down, it goes lower, lower, lower until it gets to about 0. at about this place right here, and then it goes negative, and then it comes back up. If I wanted to see it in more granularity, I could do this. I can go up here and change the number of points. So let's go to this. I'm going to change it to 25 points. So GCC, calculus, and now let's take a look at this. So I'm going to take this, and I want my slide on there, and I want to put this over here. The tabs got a little messed up, but you can really see it's like it starts at 1, goes down to about 0, and then it starts getting negative as it goes over this hump, and then it goes down, and then it's negative for a while, and then it flattens out, and then it goes back up, and it ends at 1. Now, beware of the last point. The last point in here, if you remember, what we're doing is we're looking at the element we're at plus 1. And so once we get to the end of the array, we're accessing the next element in the array, but we haven't set that up yet. So this is outside of the range of our array. So you get a wacky value. It's basically going to take the value from some piece of memory that's uninitialized. So beware of that. One trick is if you know it's a periodic signal and this is one period, you could just copy the value from element 0 into here, or you could just delete it and put something like 000 or 99999, something that is obvious that it's not going to be the right answer. That is the derivative. Nice job, you did calculus. Okay, let's do some more calculus. The other part of calculus is what's called an integral. Now, an integral in its simplest sense is really just the area under a curve. And when you take calculus, you'll learn how to do math in order to find that area under a curve for a continuous function. However, we don't have a continuous function. We have a discrete function, meaning it's made up of discrete points that exist within a time series. One array holds time, one array holds the actual voltage or the actual dependent variable. Think about the area under a curve in this context. First of all, you can use something called the polygon method, which simply draws a little rectangle and roughly tries to approximate the area under the curve at each of the time points. And if you did this, you would get an approximation for the area under the curve based upon these polygons. However, or not however, the cool thing about this is that if you then added more points, like let's say you went from n is 10 to 25, now all of a sudden the polygons get squished and you have a lot more polygons and they actually become more accurate. If you made this 1,000, you would get really, really accurate because each polygon, you could think of it as like this little slice of a line. And if you let the number of points go to infinity, you would have the perfect solution. Once you let it go to infinity, that's real calculus on continuous functions. That's not what we have. We got discrete points. So we are going to draw polygons. We are going to do the polygon method to find the area under a curve for the sine wave. Okay, I'll give you a little hint. What's the area under a curve for a perfect sine wave under one cycle? It's 0 because you have an equal amount of area on the top and then an equal amount of area on the bottom, which is negative. And when you sum all these areas up, you get a big old 0. That's all right though. All right, so here's what we're going to do. This is actually relatively simple to do because we have the point, right? We have a point and we have, so if you look at this point right here, this represents the y-axis. This is how high up you go. And what is basically the width of this polygon? The width is nothing more than a t-step. So all we need to do is multiply the delta t by the value we're at, and that'll give us the polygon. I mean, it's awesome. All right. Let's do it. So one of the things I want to do though is I want to print the poly area. So I want to print the area of each of these boxes as we go. And then afterwards, we'll just sum the whole thing up. Okay. And we know how to sum things by now. We're getting pretty awesome. All right, here we go. Here we go. Let's go down here. All right. Come down here. I found the derivative. Feeling pretty good about myself about that. Now I'm going to do find integral. And first of all, we're going to have an array that holds the area of all the polygons. So let's go ahead and fire up a little double. We'll call it Pol area. And it's going to have, of course, n points. And then we're going to do a looper. I is equal to, now this is what's interesting, 1. We're going to start at 1 and then go I is less than n points. And then I plus plus, and then begin. Now you got to be sitting there going, wait a minute. What are you talking about? Like, why would you start here? The reason is, go look at this plot. It's because this point, this is element index 0, this is index 1. So this gives us the area of the first polygon. So we basically go 1 point past, and that's the area of the region behind it. Okay. All right. So here we go. Got that. Pretty simple. So I'm going to come over here and go polygon area, and at I. And then what we're going to do is say equals. And all we're going to do is say, give me this point right here, which is evaluated. We already have it. It's in the vSign array. We've already calculated what this point is. So I simply just say vSign at index I, and then multiply it by t step. That is the area of that polygon. You cycle through using a for loop all the points, and you will end up with areas of all these little polygons. Okay. Now, here's what we're going to do. Once we're done, we're going to do this. I am now going to walk through that polygon, or that array that I just created, and I want to sum everything. So I'm going to say tot area equals 0, make a double, and then what I'm going to do is go for I equals 0, and then I less than n points, and then I plus plus. And here's what I'm going to do. I'm just going to sum every element in there. So I'm going to go tot area equals tot area plus pol area. Okay. And so this, since we initialized, let's see, tot area is 0. Okay. And what we're going to do is update that each time with the pol area. So we're just going to add, then this is the running sum, add again to the running sum, add again to the running sum, add again to the running sum. Okay. So let's see how that works. Okay. So let's make sure I got tot area equals tot area plus polygon area. We've got to get my index in there. Got to get my index. So I do that. I'm like, all right, let's see what happens here. First of all, we're not printing it, so we got to come down here and add it to our print statement. Now our print statement's getting like very big, but that's okay. Okay, so let's go all the way over here. Now what I'm going to do is I'm going to go tab again, and then I'm going to do this. I'm going to go pol area at I, but instead of I actually want to print out the decimal value of it, and then I'm going to say equal, and then I'm going to do %.3 LF for long float, and that's it. Okay, so then what I'm going to substitute in there is going to be another I and another pol area at I. Okay, all right, let's go see. Let's see if that works. Okay, so I'm going to go ahead. Let me bring this down here. You can see that print statement right there. And I'm going to go ahead and GCC this little buddy. And then I'm going to run the buddy. And now I have a ton of points. Let me go up here and shrink this point down. I'm sorry to make you car sick here. I know I'm flying all over, but video's getting long. So I'm going to pop this. Boom. All right, here we go. Okay, so it looks like what's going on is this print is getting too long for my actual console area. So I need to get rid of these tabs. So I'm just going to put spaces in between these and just kind of live with the formatting. So it's almost like the shell is like, I'm only going to let you go so far before I line wrap. So even though I didn't have a line wrap in there, it would do that. It would wrap it for me. Okay, so let me clean this all up with spaces in between, and then it should print it. Okay, so I'm going to go ahead and do this, and let me clear that, and let's see what we've got here. All right, run this thing. Okay, we got it. Now, doesn't look good because it doesn't have the tab in there, but you do get some areas under here. So let me pull this over, and let's compare it to what it should be in the slides, and let's think about what it is. So the answer is, sorry about making you sick here. The answer is we got the right answer. Okay, so that is the right answer. But now let's take a look at how that compares to the actual polygon. So the first area of this point is 0. That makes sense. The next one is 0.448. That's about right? You're up here sitting around the whole, you know, 0.6 times 0.1 area. And it's like, okay, that might be all right. And then it kind of goes up, up, up. Then it goes negative, negative, and negative, and negative. So we do have kind of the right information. Now what we have to do is once it's all said and done, we want to print. After we print that array, I want to do this. I'm going to go print F, and I actually want to do the total area is, and I'm going to do percent dot, let's go 3 precision long float, and then return, and then we're going to put in there tote area. Okay, and that is the final area under the curve. Okay, so let me get this out of your way so you can see that. So let me clear that. Let me GCC it. Let me run the calculus. Total area is almost 0. Okay. Okay, that's cool. So now watch this. I'm going to go up here and I'm going to change the number of points to be like 100. Okay, so I'm going to go 100. Now it should be like exactly 0. So I go ahead and go GCC, then I run it, and it's 0. So we actually made 100 points. The area under the curve was 0. That's very boring. So check this out. It turns out that the solution to the area under a curve over 1/2 cycle of a sine wave is known to be 2. So we can check to make sure that this actually works by only performing the time series between 0 and pi. So watch this. Let me come up here, and instead of going 0 to 6.28, I'm going to go to 3.14. And now this should be 2. This is a known answer. Like we know, we as in mathematicians figure this out, and we run it. Oh my nuggets. 2 is the area. All right, that is awesome. Think about what you just did. You just did calculus. You might not even have known what calculus was before you got in here, but you did a derivative and an integral, and it was easy because we put our information into a time series. Nice job. See ya.